It is a matter of common experience that whenever a large amount of current flows through a conductor, the conductor dissipates heat. This is called the heating effect of current. When a battery is connected across a conductor, a potential difference across the conductor sets up an electric field around it. Due to this, the electrons of the conductor get accelerated in a direction opposite to the direction of the electric field. Large numbers of electrons start moving towards the positive end of the conductor under the influence of this electric field. On their way, they collide with vibrating atoms and ions of the conductor. They transfer their kinetic energy gained from the chemical energy of the cell. Due to this transfer of energy, kinetic energy of vibration of atoms increases, which in turn increases the temperature of the conductor. Thus, when the current flows through a conductor, heat is produced. Joule's law of heating. In 1841, James Prescott Joule found that when a current I is made to flow through a passive or ohmic resistor, the heat developed is directly proportional to the square of the electric current, resistance of the conductor, and the time for which the current flows. These equations can be written as H is equal to I square RT. This statement is known as Joule's law of heating. Experimental verification of Joule's law. Joule's law of heating by electric current can be verified in the laboratory using a Joule's calorimeter. This is the Joule's calorimeter. The Joule's calorimeter consists of a nickel-plated copper vessel with a stirrer. The nickel-plated copper vessel is in a teakwood vessel. The outer vessel has a bakelite top with a provision for the thermometer. There are terminals present on the bakelite top to which a resistor is fixed. Let's see how Joule arrived at the relation H is equal to I square RT. Joule filled 2/3 of the calorimeter with m grams of water. He placed the resistor R inside the water. The calorimeter was connected to an ammeter and a rheostat as shown here. Joule noted the initial temperature of water θ1 and then passed a current I1 through the resistor for a known interval of time, say 15 minutes. Due to the flow of current, the temperature increased to θ2. He calculated H1, the heat gained by the calorimeter and water. He repeated the experiment for different values of current by varying the position of the slider of the rheostat and calculated the corresponding quantities of heat produced. He observed that H1 by I1 square is equal to H2 by I2 square is equal to H3 by I3 square. This means that H by I square is a constant, or H is directly proportional to I square. He then repeated the experiment by passing the same current I through different coils. He observed that when the same current I was passed for the same time t through coils with different resistances, the heat produced was found to be proportional to the resistance of the coil. That is, H1 by R1 is equal to H2 by R2 is equal to H3 by R3, or H is directly proportional to R. The experiment was then repeated by passing the same current through a coil of resistance R for various time intervals. He observed that H1 by T1 is equal to H2 by T2 is equal to H3 by T3, or H by T is a constant. This showed that H is directly proportional to T. These observations were mathematically summed up as H is equal to I square RT. H is equal to I square RT is the mathematical representation of Joule's law.